So in the last video, we talked about closed maps, and we saw that this projection from Pn cross y to y is such a closed map for any variety y. And so this gives us some intuition that maybe Pn has some nice analog of classical compactness in the algebraic geometry. And the correct definition here is to just take this property and say that a variety X is called complete if this projection map from X cross Y to Y is closed for all varieties Y. And then, of course, by what we saw last time, Pn is complete. And also, if you have X prime inside X, a closed subvariety of a complete variety, then X prime is also complete. And this might remind you of the statement that a closed subset of a compact space is compact. And to see this, just note, okay, Z is inside X prime cross Y, any closed subset, then we want to show its image under the projection to Y is closed. But, well, X prime is closed inside X, and then we saw the product of closed embeddings is a closed embedding, so also X prime cross Y is closed inside X cross Y. But now for this projection map from X cross Y to Y, you know this is a closed map, and then because this is closed, so Z is closed in here, and so its image pi prime, which is the same thing as the image under pi, is closed inside Y. That was what we wanted to show, and so in particular, since Pn is complete and this is preserved by closed subvarieties, also every projective variety is complete. To note that this is a special property, not every variety has this. Note that even the very nice variety A1 is not complete. And to see this, we look at A1 cross A1, mapping to A1 by the projection. And then we can write down a nice, very nice closed subset Z, which is this vanishing locus of x1, x2, minus 1. So it's the standard hyperbola like this. And then if you take the image under the projection, well, you see you get all the points except for the origin. And so even though Z is closed in here, its image is not closed in there. And so A1 for this choice of Y equals to A1, again, doesn't have the defining property of being complete. Note that this is fixed by replacing A1 with P1. Because inside P1 cross A1, like this, you can look at the closure of Z, and then taking this closure corresponds to some homogenization in this case, and then this homogenization exactly adds the missing point here. So somehow if this is the P1 direction, then it adds the point at infinity of P1, and then if you take the projection pi, you do get the origin here. So this is exactly illustrating that, I mean, this counterexample to A1 being not complete doesn't give rise to counterexample to P1 not being complete. P1 exactly adds the missing point. Okay, so a priori, if we look at this condition being complete by this projection map being closed, it sounds like a very special and technical condition, but in fact, it's exactly the right one. And we're going to see this here in this corollary. Before that, let me just briefly mention that there exist complete varieties which are not projective. So we have seen every projective is complete. It's possible to write down complete varieties which are not projective, but that's actually not so easy. It took some time to find one of these. The example was given by Nagata. And for the purpose of our lecture, basically these two things will be equivalent. And now we come to the actual very nice property of complete varieties, not just this technical statement that we heard before, but the statement that we liked, namely that if f from x to y is a morphism and x is complete, then it has all the nice properties. F is a closed map, and the image of all of x inside y is again a complete and closed subvariety inside y. So this is the analog of the statement that the image of a continuous, the image under a continuous map of a compact space is again compact. Okay. And so that proof compared to this elimination theory in the last video is actually not super hard. So first of all, let's show that the image of F is closed inside Y. Certainly, if you take the image of everything, this should be a closed set. And so for this, we just observe that, well, by definition of X being complete, this projection map here is closed. And then the crucial thing to look at is the graph of F. If you recall, the graph of F was this set of X comma F of X, where X is an X, and this is a subset of X cross Y. And then the property that Y is a variety, we have seen in this proposition, actually shows that this here is a closed subset. So it's important at this point here that Y is a variety. And then once you have the graph inside X cross Y, you can get F of X just by taking the projection of this graph, because clearly the projection, you exactly get all of the F of X for X in X. And so this is where the technical condition becomes this nice image condition. And so F of X inside Y is a closed subvariety. So there's at least something. And now we want to upgrade this, actually showing that F of X is also itself complete as a variety. And so what we need to check is that for every variety Y prime, we have a certain condition. Now, this is the scary diagram, but actually, let's just focus on the lower part for beginning. So somehow to show that F of X here, this thing, is complete, we want to show that for any variety Y prime, this projection map here, pi prime, from here to Y prime, is closed. So what we have to show is that when Z is closed in here, its image pi prime of Z is closed in Y prime. That's what we want. But now we can add a kind of roof to this diagram because, well, if you take this map psi, which is given by F and the identity on Y prime, this goes from X to F of X by F, and from Y prime to Y prime by the identity. So clearly, this here is an algebraic morphism. And the good thing is that this composition, if you go all the way from here to there, actually, this is just the projection that we like. This is just a projection to the second factor, because here we just take the identity, so nothing happened there. And then we'll just observe, okay, so we want to show that Z maps to something closed. So we want to compute pi prime of Z. But this map here, this psi, is a surjective map, right? Because X to F of X is surjective and the identity is surjective. And then for a surjective map, you can always replace Z by first taking the pre-image and then the image again. This is just basic set theory. But now if you look at this composition here, you see you have the pi prime composed with psi. This is this composition. This is exactly the big projection map pi. So we just replace this composition here by pi. And then let's look at what we have. We have that this inverse image under psi of Z is closed because Z is closed in here and psi is a morphism. So the pre-image is still a closed set. And pi was a closed map because X is complete. And so this is something closed by the definition of a closed map. And so this thing here is closed in there. So this shows actually the image is not just a closed subvariety, but is actually complete. And then the last part is now not hard. We want to show that it's F is actually a closed map. It sends any closed set to a closed set. But if V inside X is closed and X is a complete set, then we had seen in this example that V is actually complete itself. And then F of V is the image of, well, this composition. First, you take the closed embedding from V inside X. And then you take the map from X to Y given by F, right? but the domain of this composition, this V, is a complete set. And so the image of something complete is always closed by the first part, by this part which we proved here. So f of v is also closed. And so we have completed the proof. Okay. So this shows that complete varieties are really nice. They map to other complete varieties. They cannot have these pathologies that we saw before of their images being some constructible set. And maybe here as an exercise, if you note again the precise conditions of this corollary, it says it goes from some complete varieties to some y, which is a variety. And it's really important here that y is a variety and not a pre-variety. And this is a kind of exercise where you can check this this importance, and the right pre-variety to get a counterexample is the so-called projective line with two origins. So we had seen before, if you glue two copies of P1 of A1 away from the origin, then you get the affine line with two origins. And you can generalize this construction that we gave before to glue two copies of P1 along P1 minus the origin, and then you get a projective line with two origins. And then the second part of the exercise is to show that if you take one of those copies of P1, this still maps to the glued variety or the glued pre-variety. And the claim is this is a map, this P1 mapping to the projective line with two origins is a map from a complete variety to a pre-variety, but the image is not closed inside X. So it is important that the target is separated. Okay. And for a small application of this notion of completeness, recall that in complex analysis, again, we make some analogy to the complex situation. In complex analysis, we have the statement that if you have a holomorphic function from P1, the Riemann sphere, to the complex numbers, then, well, you realize, of course, because this is compact, the image is compact, so it's bounded inside the complex number. So this is a bounded, restricts to a bounded holomorphic function on the complex numbers inside the Riemann sphere. But Liouville's theorem says that if you have a bounded holomorphic function, then it's actually constant. And so, in fact, any holomorphic function from P1 to the complex numbers is constant. And this is a statement which now also can make sense in the algebraic geometry category. And below we see this kind of algebraic analog. And the algebraic analog is just that if X is a connected and complete variety, then the set of regular functions on all of X is exactly just the set of constant functions. Similar to here, set of holomorphic functions on this compact space is just the constant functions. And the proof is now also not super difficult. So let's say phi is a regular function on all of X. Then we have seen this just means that phi from X to A1 gives a morphism. Regular functions are the same things as morphisms. But this A1, of course, sits inside P1, right? So we can equally see this phi as a map to P1, which happens to land in this open set A1. It misses the infinity point like this. And now X is a complete variety by assumption. So the corollary above tells us that the image of X inside P1 is closed. But of course, it happens to lie inside this A1. So in particular, also the image of X in A1 is closed. We could also apply this thing directly again to this variant of phi. But at the very beginning of the lecture, we saw a classification of the closed subsets of A1, namely something is closed inside there if it's either finite or it's all of A1. But this case here, that phi of X is all of A1, This we can exclude because phi of x is a closed subset of A1, but phi of x is a closed subset of P1, but A1 is not a closed subset of P1. Its closure is all of P1. So this thing cannot happen. We can exclude it. So we know phi of x is finite. And we want to show it's constant, but now we can use the second assumption because x is a connected variety. And so basic topology just says if you have something connected and you take a continuous map, then the image is still connected. And then we know two things about the image. It is connected and it is finite. And the only finite and connected set is just single element set. So phi of x is equal to a. But this tells us this regular function was actually a constant function, constant equal to this a. Okay. And so we see this a priori very technical condition of being a complete variety has very nice properties. Images of complete things are complete. And this shows also that regular functions on complete and connected varieties are constant.